to the negative 6 coulombs. So then we have that divided by 12 volts. Now, if we just think about our units, this would give us coulombs per volt. So this is the number that I'm looking for. Well, depending on how we want to phrase our answer, note that thinking about this thing in terms of scientific notation, we discussed this in the previous section. We've got number stuff going on, and we have powers of 10. Let's just focus on the number stuff that's going on, not the powers of 10. I could do 3 divided by 12 and get 0.25. So I could express this thing as being 0.25 times 10 to the negative 6 coulombs per volt, which we could write as being 0.25 times 10 to the negative 6 farads. Now, this notation is sort of not ideal. We could do one of two things with it, depending on the context. If we wanted to put this in scientific notation, that would be one thing. We need to figure out the appropriate power of 10 there. Or chances are, I think the one that will be a little more useful, so let's do this one in engineering notation. Again, in a technical circumstance, you're probably more likely to want to utilize engineering notation, which is to think about the metric prefix. Well, fortunately, that negative 6 power, we already talked about that. The negative 6 power corresponds to the prefix there, so that would be micrograms. So this would be 0.25 microfarads. Technically speaking, this one's not in engineering notation because that number is not in between 1 and 100, but we could write this again. It all depends upon what unit you want to be thinking of. So you might be thinking about these things in terms of microfarads. So another thing you could do is go back and remember that there are, or go back to the page, there's 10 to the negative 9 farads or whatever unit in a nanofarad. So you could write that as being 250 NF, right? Move the decimal place 3 spots. Or again, just to introduce the last way of doing it, if you wanted to shift this decimal place over, what would you have to do here? Well, again, you might just think about, well, what happens if I take this thing times 10 to the negative 6? How many decimal places of movement do we have here? Well, note that we've got 6 zeros and then the 2 5. So the other way that we could express this would be, since we have to move the decimal place 7 spots to get it to where it's after the 2, we could call it 10.5 times 10 to the negative 7 farads. Again, all of these, when it comes down to it, are acceptable ways of expressing the answer. It's all just sort of dependent upon context, which of them is more useful for what it is that you want to be doing. All right, so everything we've done thus far is talking about ratios. Now we're going to get into what is a proportion. Well, we did equations in the last couple of sections. A proportion is just another equation, but in particular, it's going to be an equation that looks like the following. Some fraction, a over b, equals to another fraction, c over d. And in this circumstance, we are going to, of course, specify that neither of these numbers is 0 because dividing by 0 is a big mathematical no-no. So again, what this equation is saying is really just saying you've got one ratio, a to b, and it's equal to another ratio. So those two ratios are equal. Very often we use these proportions to describe a relationship between rates, and if two rates are equal, if we have some number of miles per hour equals some other number of miles per hour, we need to make sure that the units are in the same order for both of those fractions. In other words, we just need to set this thing up mindful of what the rates are that we're dealing with. Now, a lot of times, to solve a proportion, we might need to do some math. We've kind of done a little bit, but it shows up often enough that we're going to give it its own name. We can multiply both sides by both denominators. In other words, if we had this equation like here, a over b is equal to c over d, we could multiply both sides by b and multiply both sides by d. Let's just explore what would happen if we did that. So if we multiply this thing by b and d, and then also multiply the right side of the equation by b and d. Well, on the left side, the b factor will cancel, and on the right side, the d factor will cancel. So this will say, oops, I didn't write equals. So this would say that d times a, or I'll write it as a times d, is equal to c times b, or b times c. In other words, the process that this is called is sometimes cross multiplication. When I take this proportional equation here, I can rewrite it without fractions entirely by noting that a times d is equal to b times c. So essentially we're taking the product of that diagonal with the product of that diagonal. I personally don't really like to think about it in that way because it obscures the fact that really all that's going on is you're multiplying both sides by both denominators. Once you have it in that format, now you just go ahead and isolate the desired variable, which is really just going to mean divide, right? If I wanted to solve for a, I could go ahead and divide both sides by d. That would give me my answer. So let's see some applications in which we might want to use one of these proportions and talk a little bit about problem solving. I wanted to throw in an extra little thing in here. One way we can use proportions is actually to revisit unit conversion. So let's say we wanted to find the number of inches in 47 centimeters. Now we talked about how to think about this in terms of multiplying, but in other circumstances, we think about these things in terms of like a scale factor. So like a diagram might be in a certain scale, for instance. So let's say we have this ratio here that 1 inch is 2.54 centimeters. And I could set this thing up as a proportion. So when we're looking at a problem like this, we could start talking about the problem solving process, and then we'll use that to actually discuss this particular problem. So the first thing that we need to do is understand what the heck's going on, right? We need to go ahead and read the directions here, read the statement of the problem. Again, I know that in this class it's a sort of artificial circumstances that are made up, but when you're actually using math, you need to figure out what the heck is it that I'm trying to find. Is it an unknown voltage? Is it this amount of lead that's in someone's blood, etc.? So we need to figure out what the heck we want to find. And generally speaking, what that means is we want to figure out what is it that we know and what is it that we don't know. And then we want to go ahead and come up with a plan to solve this problem. So in the case of proportions, we want to set up an equation. And when we're setting up that equation, we want to make sure that the units match, right? That the order of those units matches. That's going to be particularly relevant for this one. Next thing we want to do is go ahead and actually just do the thing we planned. So we're going to carry out the plan, just solve the problem, right? In the case of a proportion, you need to isolate the variable, and you might need to use that thing we just introduced, this idea of cross multiplication. The very last thing that you need to do is something we've talked about before in the context of solving equations, which is going to be check your answer. Now we're going to take it a little bit further than we did before. In the previous one, we just plugged the number into the equation and made sure it worked. In this case, we actually want to check and make sure, does this thing make sense? Like, or did we set up the equation wrong? If we set up the equation wrong, the answer is going to be garbage. When we're expressing our answer, we want to make sure we include units if that's a relevant thing to do. So again, coming back up to this one, the number of inches in 47 centimeters. Well, we know that we have 47 centimeters. The thing that we don't know is the number of inches. So we could say that there's some number x inches relative to that 47 centimeters. In other words, there's some number that I know that measures this thing in terms of inches. And we know that that ratio has to be equal to the fixed ratio that converts inches into centimeters, that there is exactly 1 inch in 2.54 centimeters. Note that when I've set this equation up, I've made sure to ensure that the units are in the right spot. In fact, I really like to actually explicitly write down my units just to make sure I didn't accidentally put them in the wrong order. And it's one of those things that you can't necessarily just read the problem and know where they have to go. You make a decision of how you want to set them up, and then ensure that you put all the units in the right spot. Now let's think about the simplest way to solve this problem here. I've got the thing that I want, the number of inches, being divided by that quantity 47. The easiest way to solve this equation would simply be to undo what's happening to x, right? The thing that's happening to x is it's being divided by 47. So all I need to do is go ahead and multiply by 47. We'll go ahead and assume that this is an approximate figure that we're dealing with here. So we've got 1 divided by 2.54 times 47, right? And the other side is just simply x. So if we're dealing with an approximate number, that means we've got 2 significant digits. So I'm going to express this answer in terms of 2 significant digits as well. So have to round it up just barely. And of course, we're going to express this answer in terms of units. Now, the last thing we could do with this problem would be to just double check, does this make sense? Well, I have here that 47 centimeters corresponds to a smaller number of inches, and that makes sense, right? There are going to be, in the same object, more centimeters in that object than there are inches in that object. Let's explore another topic. It's actually something we did a couple of sections back, and now we can look at it in its full glory now that we've talked about variables and equations, etc. Coming back to this transformer equation. So transformer equation says that the voltage across a coil is proportional to the number of turns in the coil. So this is often phrased as Vp over Vs equals Np over Ns. This shows up in a lot of practical circumstances when you try to figure out how to design a particular circuit. So let's say we want to use this equation to figure out how many, I should say the number of turns, sorry about that, number of turns required in a secondary coil N sub S to get a secondary voltage of 12 volts. So we have some desired voltage. And let's say that we have our primary coil of 32 turns generating a voltage of 9.0 volts. Well, we've got some quantities here that are known, some quantities here that are unknown. So let's just go ahead and, again, we've read the problem. We have this proportion. Fortunately, we already have the equation given to us. In other circumstances, we'll need to create it. But we have this equation. It looks like my secondary voltage that I want is 12 volts. My primary coil, so the number of turns in that primary coil, N sub P, is 32. And the voltage that's associated with that, the primary voltage, is 9.0 volts. Note, by the way, all of these things, 2 significant digits, so our answer is going to have 2 significant digits as well. The thing that we don't know is the number of turns that we want in our secondary coil. So let's go ahead and plug in all of the values that we have and use them to find that missing value here. So NP is 9.0, and then that's over 12. I guess I could call that 12 volts here. We got 9.0 volts over 12 volts is equal to 32 over the thing that we don't know. Now, actually, don't need to keep track of the units here. You can note that the units would sort of cancel one another out, so they're not something we need to worry about. And the answer that we're going to get here is going to correspond to some number of turns, how we actually need to design this coil to get the desired effect. Well, here, this is an illustration of, we've got a variable in the denominator. So since we have a variable in the denominator, we'll want to go ahead and use that cross multiplication to get rid of the fraction. So cross multiplication says that the product of these two things will equal the product of those two things. Or the other way of thinking about this is we multiply both sides by 12, and we multiply both sides by ns. So that's going to tell us here that 9 times ns, I can skip the 9.0 for computational purposes, is going to equal the product of these two things, 32 times 12. Now to isolate the variable, we've explored things like this before. We just need to go ahead and divide by that 9. So we get 32 times 12 over 9. Let's see what we get. 32 times 12 over 9 gets me like 42 point something, 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 something. Well, if we want to go ahead and round this thing, that's going to tell me I will need 43. In fact, if we're talking about a number of turns, we might actually just need to have a whole number. We might not get exactly the voltage that we want, but maybe it'll be close enough. Again, in most technical circumstances, it's really just a question of getting good enough. So here, that will tell me 43 turns. Well, let's just check to see if that makes sense. Again, now we have an actual context for understanding this. Basically, what this equation says is that the more turns you have, the higher the voltage. So if 32 turns gets you 9 volts, it would make sense that you would need a few more turns to get a slightly higher voltage out of that. So there we have it. Let's look at 2 other examples where we're actually going to have to follow this problem-solving process a little bit more and actually set up what it is that we want. So more things that I had fun looking up. A Tesla Model 3 has a battery that has a capacity of 82 kilowatt hours of energy, and it has a purported range of 353 miles. So then we might ask, if the battery is only charged to 11 kilowatt hours, what would its range be? We're going to go ahead and make this assumption for right now that the range is proportional to the energy uses, or the capacity. In reality, it's actually a little bit more complicated than this, but let's just try to keep it simple here. So it looks like, again, we have 3 quantities that we know. We know the total capacity of this battery. We know the current capacity here that we're talking about, 11 kilowatt hours, and we know the total range. There's actually a little bit of leeway and freedom that you have in terms of how you set it up, but one way that I think makes sense is to say kilowatt hours per mile, or miles per kilowatt hour, either way, really. But what we could say here is we have 82 kilowatt hours, kilowatts, a capital W, over 353 miles. Again, what was the thing that we don't know? We were asking this question of how far, so let's say that our distance here, got to give it some variable. I'll just pick x, right? You can pick whatever letter you want, but x is sort of our default way of thinking. So I'll say that the distance here that I don't know is x. Well, the way that I set up this ratio, again, I have this known ratio of 82 kilowatt hours relative to 353 miles. Now, the quantity that I know here is the 11 kilowatt hours. So that known number has to go up top, because we can't have kilowatt hours per mile on one thing and then miles per kilowatt hour on the other side, because it's completely different things here. It's comparing 2 completely unrelated quantities in a certain sense. So instead, we need to go ahead and, the way we've chosen to set this up, put x miles down here. Again, there's actually like about 5 other ways I could have chosen to set this up and other ways to solve this problem, but this is a way we can do this with proportions just because it's a standard way. When you see one proportion, you pretty much see them all. It's kind of the same way of doing any one of these sorts of problems. So we can solve this thing using cross multiplication because that variable is sort of trapped down there. So cross multiplication says that 82 times x will equal to 11 times 153. Sorry, excuse me, 353. Again, I don't need to keep track of the units at every single step so long as I keep track of the units at the beginning to make sure I've set it up correctly, and keep track of the units at the end to make sure that I'm reporting an answer that's meaningful. So here x will be, again, to get it by itself, we've done a bunch of these things, we're experts in this by now, divide both sides by 82. What do we get? 11 times 353 divided by 82. Looks like, in terms of significant digits, I got 2, 2, and 3. I gotta go with the least accurate one, which is gonna be 2 significant digits, so we report this as 47. What the heck was it that we were trying to say? Oh, well, distance was x, so this represents a distance, and oh yeah, we said that this was a number of miles. So this would say that with 11 kilowatt hours, we could travel 47 miles in this thing. Last thing we can do is just ask ourselves, does this make sense? Well, 11 kilowatt hours is kind of a small fraction of 82. It's like an eighth-ish of that. So it does make sense that the range that we're talking about is a relatively small fraction, certainly less than the range that we have, but it's about something like an eighth-ish. So this seems like a reasonable answer. One last thing we'll talk about in terms of ratios is talking about dosage calculation. So dosage calculation is a huge important thing in the medical community because you need to make sure that you give people the right amount of drug. And when it comes to giving a person a certain amount of drug, usually it's done relative to the body mass that that person has. This is particularly relevant when it comes to things like children, because children start off being tiny little creatures and then grow to be significantly bigger. So there's different guidelines depending on the child's body mass. So a guideline that I found here is that when it comes to prescribing acetaminophen, there's 5 milliliters of acetaminophen prescribed for every 25 pounds of the child's weight. Now, of course, with acetaminophen, when it comes to like just dosing it, usually they'll just have on a bottle. If your kid's in this range, you give them this amount, etc. But a lot of drugs, we need to be very, very precise with how much we give people. So we need to perform a little calculation to make sure. So this one's a slightly lower gravity example, but the principle is the same. We've got some fixed ratio, 5 milliliters relative to every 25 pounds of weight. So again, the desired ratio to be administered here is 5 milliliters per every 25 pounds. That is the known ratio that we have here. And the thing that we're trying to find is we've got X milliliters that we want to give to Zoe here. So again, setting up this equation, the unknown here is the number of milliliters. So since I set up this ratio over here in terms of milliliters per pound, I want to make sure the equation on the other side is also milliliters per pound. Well, again, we don't know the number of milliliters that we want here, but we do know the weight is 65 pounds. Let's think about the easiest way to solve this. We could use cross multiplication. There's nothing wrong with using cross multiplication. But if we think carefully about what we need to do to find x, x is currently being divided by 65. So if we want to undo that, undo division by multiplying. So we will multiply both sides by 65 again. The purpose of doing that is it'll cancel out the terms on the right-hand side. And x will be equal to this product here. So 65 times 5 divided by 25 actually works out to be an exact number here. So that works out to be 13 milliliters. Very last thing we can ask is, does this seem reasonable? Does it make sense? Well, yeah, if you got 25 pounds is 5 milliliters, certainly 65 pounds is going to have to be something a little bit more than 2 times that. So 13 milliliters, sure, that seems reasonable. All right, so that gets us through all of this stuff. Again, all of these things that we've been doing, problem solving, using equations, thinking about units, all of this is stuff that we're going to be doing throughout this course. So they're useful skills to have in mind. When we pick up with the next section, we will be in a different unit talking about geometry. So I will see you then.